Hi, this is week 2 of our class on how to compute power for cluster randomized trials or multi-site trials. This is Michael Borenstein, and my email address is michaelb@poweranalysis.com. My agenda for this week is as follows. The video is pretty much going to parallel the PDF that you should all have. We're going to talk about how to save scenarios within the program, the reasons for using blocking at the top levels, and how to do that using the program, the option to use covariates at one or more levels. We're going to spend some time speaking about the difference between fixed effects and random effects statistical models. I'm going to spend some more time showing how to use the graph, which I think is a very important feature in any power analysis, and I'll show you how to do that in this program. And finally, I want to spend a little bit of time talking about the different ways of defining the effect size for continuous data in a cluster randomized trial, and how that differs from defining the effect size in a simple randomized trial. So let's get started. So I'm going to start the program over here under levels. I'm going to right click, enter the names of the levels, schools at the top level, students at the second level. I click OK, and over here I have schools and students. By default, these are randomized at the schools level, which is what I want. Under effect size, I'm going to choose standardized mean difference, D total, which means that we're standardizing by the total standard deviation, and the effect size we're going to set at 0.5. Rather than span of means, I want to enter the ICC, so we're going to set that at 0.07. Down here, we want to give the span of student scores within a school, and we decided that we need to set that at 386. We want to set the mean SAT score for the control group at 500, so I click over here, I type in a value of 500 and click OK. And what we see is that the student scores within a school are going to range from about 307 to 693. The school means are going to range from about 447 to 553, based on the ICC and based on the span of student scores. We've already explored this last week, don't really need it today, so I'm going to come up here, click ICC, schematic always off. You'll notice the options are always on, automatic, and always off. Automatic simply turns this on whenever we're entering values for an ICC. The next thing is, let's go ahead and reset some of the number of units based on what we had last week. We're going to say that we have 11 schools for each treatment and 20 students for each school. We'll go ahead and enter the costs that we were using last week. We came up with costs of $2,000 per school and of $50 per student. I can right click over here, and rather than displaying the power as a bar graph, we can actually show the number, which is 9043. So this is pretty much where we left off last week. The effect size is 0.5. We have this number of schools and this number of students. This is the ICC, and the study is going to cost approximately $66,000 and yield power of 90%. Now, one thing that we can do immediately is we can save the file. I'm simply going to come over here and click Save. The program's going to ask me for a name. Let's call this week 2, and click Save, and now the file is saved. It tells me that right over here. Just the same way that you would save any other file. But one thing that we want to do, one of the things that we're going to be doing this week, is playing with different versions of this. We're going to be changing various parameters and looking at different designs. And rather than save everyone as a different file and need to go back constantly and retrieve them, the program allows you to save different versions of the design within the same file. And the way that you do that is you click on Scenarios, and then you say Show Scenarios, and the program basically opens up this box, and whenever we click Add, as I'm going to do right now, the program takes all of the information that's included over here, including the names, the number of units, the ICC, and so on, adds it in over here, and by default it's called it Scenario 0001, and it simply lists the power and the cost. The power from here, the cost from here, and all of the other information is not being shown because there would be no simple way to show that, but all of that is sort of behind this pane. One thing that we can do if we're going to keep on adding different designs is we probably want to name this and give it a description. So I click on this to highlight it, I click Edit, and I'm going to call this, let's say, the basic design, and a description would be randomize schools. And to distinguish this from some of the designs we're going to be looking at in a few minutes, I'm going to say that there are no covariates. This description, by the way, is purely a mnemonic. The fact that I've called this randomized schools doesn't have any meaning except for me. And I click OK, and then we can close this to get it out of the way. The next thing that I'd like to take a look at is blocking. What we did so far is we randomized schools. Some schools are assigned to treated, some schools are assigned to control. We use these schools to estimate the mean of all treated schools. We use these to estimate the mean of all control schools. And then at the end we take the difference between those two means. To the extent that there's error in estimating this mean, and to the extent that there's error in estimating this mean, then when we take that difference, there's going to be error in our estimate of the difference. And as we saw last time, to the extent that there's more dispersion within these and more dispersion within these, in other words, as the ICC goes up, power is going to go down. So let's bring power, the ICC back to 0.07. And the alternative over here is, rather than randomizing schools, we can block at the school level and randomize students. You see over here what had been one box for treated and one box for control now becomes a single block that's marked blocked. And let's say, for the sake of argument, we put 7 schools in there. What happens now is what we're taking from each school is not the mean of the treated group or the mean of the control group. What we're taking from each school is the difference between treated and control within that school. So if we happen to have a school with a very low mean, it doesn't really matter, because we're not using that school to estimate the mean of the treated or the mean of the control. What we're doing is we're using that school to estimate the difference between treated and control. And to take an extreme example, if that difference, if the impact of the intervention is always 50 points, so we happen to have a school with, let's say, a mean of 300 rather than 500, the means in that school are going to be 300 for treated, 300 for control, and 350 for treated, a difference of 50 points. At the other end, if we happen to have a very high-performing school, then in that school, the means for control and treated might be 650 and 700. Again, a difference of 50 points. Because what we're taking from each school is not the school mean, but simply the difference between treated and control within that school, then the fact that the mean varies from school to school is not going to be a source of error. And therefore, we can generally get higher power when we use blocking as compared to when we randomize at that level. While it's true that we are basically getting rid of the sampling error that comes from the fact that the means vary, we're trading that kind of sampling error for a different sampling error. The sampling error that we are getting is going to be based on how much the treatment effect varies from one school to the next. So let's say that what we have over here is the span of the treatment effect. We've said that overall the mean treatment effect is 0.5, and which corresponds to a raw difference of 50 points. If it was the case, if we had reason to believe that every single school would have exactly the same mean difference, then we could get very good power by having as few as 1 or 2 schools, because whatever the difference is in those schools, that would give us a very precise estimate of the difference in all schools. In reality, that's not going to happen. In reality, what we have might look something like this, where the effect size is going to vary from school to school. And let's say that the span of effects, in other words, the span of the standardized mean difference is 0.5. That would mean that if the overall, the grand mean of the standardized mean differences is 0.5, then we're going to have some schools where the standardized mean difference is 0.25 and some where the standardized mean difference is 0.75. Or in raw units, if the average is going to be a 50-point difference, there are going to be some schools where the difference between treated and control is 25 points, and some schools where it's 75 points. So now we can no longer say we're just going to pick 1 or 2 schools and get a precise estimate of the treatment effect in those schools, because there's no guarantee that the effect size that we see there is going to be a precise estimate of 0.50. We might happen to grab 1 or 2 schools down here so that our mean effect size is going to be closer to 0.25 or 0.30, or we might grab a couple of them up here so that our estimated effect size is going to be 0.70 or 0.75. The only way that we can be assured of getting a mean effect size someplace near 0.5 is by having a lot of schools. And this is exactly parallel to what we saw before when we randomized at the top level, to the extent that there was a lot of dispersion from in school means. We needed a lot of schools to address that. And now over here what we're saying is that to the extent there's a lot of dispersion in treatment effects, we're going to need a large number of schools to address that. What we see over here is that with 7 schools, if we're assuming that the treatment effects span 0.5, then with 7 schools, we're going to have power of 91%. On the other hand, if the treatment effects span, let's say, 1.0, so that they range from some schools where the treatment effect is 0 points, others where it's 50 points, and others where it's 100 points, then with only 7 schools, power would drop to 0.79. But if we increase the number of schools to 9, from 7 to 9, then we've addressed that extra dispersion and power is back up around 91%. I should take a moment and point out that this graph over here is really very, it can be very useful. Before, when we were dealing with ICCs, I showed how we can look at that, and we can say that an ICC of 0.07 corresponds to a span of means of students within schools of this sort, and a span of school means of this sort. So we have a way of ensuring that the ICC that we're looking at corresponds to our expectation of how the school means are actually going to vary. Similarly over here, if we say that the span of effects is 1.0, and we look at it and we say, well, this corresponds to a situation where some schools are going to have 0 effect and some are going to increase the score by a full standard deviation, we can then ask ourselves if that's plausible or not. I mean, we might look at that and say, well, you know, this treatment effect might not be exactly the same in all schools, but it's always going to be at least 0.20. We can change this to bring it back to the point where the treatment effect ranges, let's say, from 0.20 to 0.80, so that we, again, can just be sure that the numbers that we're putting in over here are plausible. Let me bring it back to 0.50, which I think is the example that I was using earlier. I want to point out two other things. First of all, if I bring this back to 0.50, Power is now back up to 0.97, and I can bring the number of units, number of schools back to 7 and still have power of greater than 90%. The other thing is that when we've blocked at the top level, the ICC really has very little impact on the power, so that I can increase the ICC. Power is now 0.91, and if I was going to bring the ICC up to 0.20, power is not going to go down at all. It appears to be going up, and actually it is going up. That's for a technical reason that we can discuss later on in the course, not having anything to do with error, actually having to do with the way that the effect size is being computed. But the key thing is that this source of error is no longer hurting the power. Regardless of where we set the ICC, power is going to remain basically in the same ballpark. Okay, now that we've set the span of effect and we have the effect size, we want to find out what's the most cost-effective way of getting power of 90%. Let's say that the cost of each school is $2,000. We can then make sure that we set the desired power to 90%. We click the Optimal Design Wizard. The Optimal Design Wizard tells us that the most cost-effective ratio is going to be a ratio of 35 students for every school. And so we click Paste. It puts those numbers in, and it shows us that we can get power of greater than 90% at a cost of $33,000. And this compares to the $66,000 that we were looking at a little while earlier for when we had randomized schools. So we're saving a substantial amount. As before, we might want to go back and tweak this number. And the reason is that when we use the Optimal Design Wizard, it gives us the best possible, the most cost-effective possible ratio. So that's the first thing that it does, is it sets the number of students per school. Having done that, it then says, okay, with 2 schools, what would the power be? With 3 schools, what would the power be? And it keeps on going until it exceeds 90%. In this case, not only did it exceed 90%, but it actually bumped power up to 95%, because with 5 schools, power was 88, so it goes to 6 and power is 95. If we allowed the program to put in a decimal value over here, for example, to say that we need 5.1 schools to get power of 90%, then the numbers that it's coming up with would be exactly the best possible ratio. However, since we're forcing the program to jump to the next higher integer number, in effect what it's done is it's jumped over 0.90 and gotten as high as 0.95. And the cost is $33,000. But once we've exceeded the number that we actually need, we're using 6 rather than 5.1 or 5.2, we actually have a little bit of flex room over here. We can reduce the number of students and bring power down while still keeping it above 0.90. So I'm going to just tweak this a little bit, and I can bring the number of students down to 26, and then we have power that still exceeds 90%, but it costs only $27,000. This happens to be an extreme example. Generally, increasing the number of schools by 1 is not going to increase the power by 5 or 6 percentage points. So generally, this idea of tweaking is going to be relatively less important. But I simply wanted to explain to you what's happening over here, because if you understand that, you do have the option of reducing the number of students and bringing the cost down by doing that. Now that we've done this, let's go ahead and save this. I'm going to click on Scenarios, Show Scenarios, Add the Scenario. I'm going to click on this one. I'm going to say that I want to edit it. I'm going to call it Blocked, comma, no covariates. I'm going to give it a more descriptive name of Blocked, no covariates. Click OK. So what we have over here so far are 2 options. When we're not blocking, in both cases, power is about 90%. The cost in one case is $66,000. In the other, it is about $28,000. I'm going to close this. And if I wanted to go back and compare these scenarios in more detail, I can click on Basic, Restore, and I'm back to the first option. I can click over here, Restore, and I'm back to the second option. Let's go back to the first option for a minute. I'm going to restore it. The other thing that I do need to remind you is that you have to now save the file, which it just did, because until you save it, the different scenarios are only being held in memory. They haven't actually been written to a file. Let's close that, and then we're going to come back in a second and look at the option of adding covariates. The next thing that I'd like to do is to take a look at the use of covariates. First, I'm going to do that using the case where we randomized schools. So for those of you that don't have this on your screen yet, you can go back to Scenarios, Show Scenarios, and if your screen looks like this, where we were dealing with the block design, you click on the top level, you click Restore, and now we're back to this design over here, and then we can close this. You'll recall that we had 11 schools for each condition, and that within each school we had 20 students. Power was about 90%. The cost was about $66,000. The idea of using covariates is that we can reduce the error term at each level. In the case of schools, the error came from the fact that the mean varied from school to school. But if we can explain away some of that variance, then we can reduce that source of error. And it might make sense to think that if we have, since what we're looking at is how the SAT score varies from school to school, if we know the school's if we know the school's SAT score from the previous year, then we can probably use that as a covariate in predicting what the SAT score is going to be this year. Similarly, if we have a second covariate, which might be the school's ranking the previous year, again, that might be used to predict the SAT score this year. So I've put in two covariates. One would be the school's mean SAT score the prior year. The other one would be the school's ranking. We are suggesting that those two together can explain 60% of the variance. And by putting those two covariates in, we now have increased the power to 98%. Similarly, there might be covariates at the student level. What we're trying to do is to predict the score of a student within his or her school, and it makes sense that each student's GPA, let's say, from the previous year would be a predictor of what their SAT score is going to be this year. So let's say we have one covariate, and let's say that we expect that's going to explain 40% of the variance. So basically what we've done is by including two covariates over here and reducing this error term, and by including one covariate over here and reducing this error term, we've been able to increase the power to better than 99%. Since we don't need power to be quite that high, we can now reduce the number of schools and or the number of students and still have power of 90% at without spending quite so much money. To find the best way to do this, we'll click the Optimal Design Wizard, we'll say Compute, and the program says that the optimal design is going to be 28 students per school. We can click Paste. I'm sorry, I had neglected to tell the program that we want power of at least 90%, so let's click 90. Now click Compute. It says the optimal ratio is going to be 28 students per school, and we're going to need 6 schools. I click Paste, and it gives me power of 93%. Again, what's happened over here is that we've jumped over 90%. With 5 schools, power would be 85. With 6 schools, power is 93. Again, a somewhat unusual situation, but since we're dealing with such a small number of schools, each additional school has a major impact, and we can come back over here and tweak this a little bit so that we see that we can actually get power of 90% with 22 students per school and 6 schools. Now we can go ahead and save that. We'll show the scenarios. We'll add this one. We'll click over here and edit the name, and we'll call this, let's say, basic 2, and this is randomized schools with covariance. Click OK, and we will close this. Just to take a minute, the impact of the R square is going to depend on what the ICC had been. In other words, if there had been relatively little error over here in the first place, if the ICC had been closer to 0, then there would have been relatively little error over here, and therefore adding the covariance would not have made that much of a difference. Conversely, if we had a lot of a very high ICC and a lot of variance, then this would have been relatively important. So the impact of the R square is going to depend in part on the ICC. It's also important to understand that when we open the optimal design wizard, I think I probably explained last time that when the program is trying to find the most cost-effective ratio, a key factor in that is the ICC. To the extent that the ICC is high, that means that a relatively high proportion of the error is at this level rather than this one. And that tends to shift the ratio towards having a smaller number of students per school, because what we need to get is not more students, what we need to get is more schools. When we add an R square, then whatever the ICC at this level had been, in effect, the impact of that immediately comes down. So that if the ICC is 0.07 and we have an R square of 0.60, the effective ICC is going to move down maybe to the area of 0.04. And when we do that, since now the location of the error shifts away from here and back to here, that's going to change the ratio so that we're going to need more students per school. Or another way of looking at that is that we're going to need more schools and not quite as many students. So the ratio that it's finding over here, let's actually go back and take a look at that. When we say compute, if the R square is, let's bring it down to 0 for a second in both cases. And when we look for the ratio, the best ratio is going to be 23 to 1. 23 to 1 is the ratio, and then we need 11 schools using that ratio to get power of 90%. But the ratio is 23 to 1 because there is a certain amount of error over here. If we increase the R square so that we have relatively less error at the top level, then when we go to ask for the ratio, instead of being 23 to 1, it's 36 to 1. Because since there's less error at the top level, then we can concentrate on having more precision within schools rather than reducing the error among schools. So the ratio has gone from, I think it was 23 to 1, it went to 36 to 1. On the other hand, if we increase the R square at the student level, which we're doing up to 0.40, then the ratio is going to shift back, so now it's 28 to 1. So the point is that when we're trying to find the optimal ratio, we're always working with the ICC, but that these R squares in effect modify the impact of the ICC. Of course, in both cases, the ratio also takes into account the relative cost of students versus the relative cost of schools. So all of these factors, the ICC, the covariance, and the costs go into the process of figuring out the optimal ratio. So far we've seen how blocking can increase the power and how the use of covariance can increase the power. We can use both of them at the same time, or I should say if we can use both of them at the same time, because it's not always possible to use blocking. That's going to depend on the substantive nature of the project. But if I go to scenarios, show scenarios, let me open up the one with blocking. I'm going to restore that. We had 6 schools with 26 students, 26 control students and 26 treated students within each school. Power was about 90%. The cost was about $27,000. Let's say that we can introduce covariates at the student level. We're going to have the same covariate we had last time, which is the student's GPA score from the previous year. And let's say with that explains 40% of the variance in student scores. That would bring power up to about 98%. We can then use the optimal design wizard and say compute. The program's going to tell us that the optimal ratio is 27 students to each school, and that we're going to need 5 schools to get power of 90%. And then again, we can come back over here and tweak that a little bit. We find out that we can actually get power of 90% with 23 students per school. So the cost is down to $21,500. Let's save that. Over here, we're going to click on this. We can edit it. We're going to call this blocked with covariates. Click OK. And what we see is that we have now a range of costs. Power in all cases is about 90%. We have one design where we can do this for only about $22,000, another one where it's $66,000. So there's a range of about 3 to 1 as far as the costs. I should say something about the idea of blocking. Blocking is not always possible. If the intervention that we're using is something that can be done at the level of the student, then blocking might be possible, and it probably would make sense because it's going to save a lot of money. But if the intervention that we're doing is something that has to be done at the school level, for example, let's say that we are offering some kind of after-school tutoring, and that we expect that the students that take advantage of this are going to have an increased score, it might be very difficult to offer that tutoring to some of the students and not others, because the parents of the students that are not getting the intervention are going to be understandably very upset, and therefore that might not be an option. Even if we're offering an intervention that might take place at the student level, perhaps giving some of the students some kind of material that they can study on their own, there might be the possibility of cross-contamination, where students are going to share these materials with their friends. And therefore there are many cases where the intervention has to be at the school level, and therefore blocking is not an option. But as I said before, when blocking is an option, it typically turns out to be a more powerful solution for the same amount of money. So we've saved this. We can come back over here now and save the whole file so that all of that is available to us the next time we want to open the program. One more thing, you also can have covariates at the school level. In this particular example, it turns out not to be a good idea. And the reason for that is as follows. Notice that power is now 90%. If I say that I'm going to add one covariate, before I've done anything with the R square, just by increasing the number of covariates from 0 to 1, power is going to drop from 90% to 82%. And if I put in a second covariate, power drops to 63%. Once I actually add the R square, power is going to go back up, but not that far. If I bring the R square back up to 60, power is now still only at 68%. So in effect, what I have done is by adding 2 covariates, rather than increasing the power, I've managed to hurt it substantially. Well, this might seem counterintuitive. The reason is that we're dealing over here with only 5 schools. And so the degrees of freedom for the test initially is 5 minus 1, which is 4. which is a very, very small number of degrees of freedom. For those of you that normally think about primary studies when you're doing a t-test, we learned way back that you probably want to have at least 30 subjects, because below that, the degrees of freedom is so small that the t-test is just going to be, you're going to be dealing with low power. Similarly over here, if we have only 4 degrees of freedom, that's really pretty poor. And for every covariate that we add, we lose 1 degree of freedom. So whereas the degrees of freedom with no covariates had been 4, with 2 covariates, it's only 2. It's 5 minus 1 minus 2, which leaves us with 2. And with that few covariates, the power is going to drop. The question is whether or not we can offset that by increasing the R square. And in this case, even if the R square was up at 0.99, we would not be able to undo the damage that we did with having so few covariates. Again, this is a relatively unusual case. If we had, for the sake of argument, 10 schools, let's say we were dealing with a smaller effect size, and we needed 10 schools to get power of 90%. Let me bring this back for a second. And let me change the example a little bit further. Let's say that we had an effect size of 0.2, so that initially we were dealing with 19 schools. In this case, adding 2 degrees of freedom is going to have virtually no impact on the power, and adding an R square will actually help us quite a bit. It brought the power up from 90% to 94%. So I guess what I'm trying to show over here is that every case is unique, and you should never be doing this by rote. You can't say, well, we have, we're simply going to add covariates because covariates help. In the vast majority of cases, they do, but we happen to be dealing over here with a situation where they don't. So just as you would never go into an analysis and just to sort of do everything by rote, you really need to go back and look at the data and make sure that everything makes sense. Similarly, in doing a power analysis, you have to look at each of these things as you think of applying them and make sure that they actually are increasing the power where you would expect them to, and if not, understand what the reason might be. Let me come back to the scenario that I had a minute ago. As a matter of fact, let me go back to this initial scenario. I'm going to click Restore. I'm going to click Close. I'm going to save this whole thing back over here, and then we can come back and look at a couple of more ways of using the program. Let me show you one more thing which has to do with the statistical models. If I come back to Scenarios and I open up the scenario for blocked with no covariates, I'm going to restore that. You will recall that what we had over here was assuming a 26 students within each school, the span of effects ranging across a span of 0.5. In order to get power of 0.90, we had to have six schools. But you see over here that there's an option for the statistical model to be either random or fixed. In general, in the program, if you're not sure what one of these options means, you can click Show Details and then click on the option. So it says now over here that the sampling model for schools is random. This means that these schools will be sampled from a larger population of interest. To select fixed, use the spin button, and we can do that over here. I'm going to bring it back to random for a second just to show that if you click on definition, fixed means that the schools in the study represent the entire population of interest. Random means that these schools will be sampled from a larger population of interest. In other words, random is what we are generally using. It means that, just as it said over here, that we're simply sampling schools. In this case, we've sampled 6 schools, and we're going to use the treatment effect in these to generalize to all schools in the state. Alternatively, we can imagine a situation where somebody is working within a particular district within the state, let's say, and there are only 6 schools in that district, and they want to find out if the treatment intervention is effective in that district. They have no interest in finding out whether it works beyond that district or not. They were hired by the district. They're not interested in doing primary research. They simply want, and finding out if this works in general, they simply want to know if this intervention is going to work right here for the kids in these 6 schools. Since we're only dealing with 6 schools, we no longer have a situation where there is sampling error at the school level. In other words, while it might be true that within these 6 schools, the treatment effect might vary, but what we're asking about is about the average treatment effect within these 6 schools. And since we have the entire population in front of us, as it were, if we can find out what the treatment effect is for these 6 schools, then we know the treatment effect for the full population. We don't need to be concerned that the true treatment effect in these 6 schools is not going to be the same as the treatment effect in the whole state, because we don't care about the whole state. So what happens is, as we moved from a random effects to a fixed effect model, I'm going to close this out. You can come back and explore these other buttons on your own. When we had random effects, and therefore there was sampling error at the school level, we needed 6 schools to get power of 90%. By contrast, if there's no sampling error there, so that we're using a fixed effect model, then even if there were as few as, about 3 schools, we'd still have power of approximately 90%. Now, obviously, there's a kind of a circular reasoning over here. I'm not saying that there are six schools in the district and then we can drop back and look at only 3 of them, but I am saying that if the entire number of schools that we cared about was 3, then with even those 3 schools, we would have enough power to do the study. And by the way, the reason that the power drops as we move from 6 to 3 is not because we are introducing sampling error. We've said that there is none. Rather, it's because we are reducing the degrees of freedom. And in this case, with 3 schools, we have only 2 degrees of freedom, and that's what's going on over here. I should emphasize, I did this in the PDF, and I want to do it again over here. You cannot say that I'm going to get better power if I use the fixed effect model, and therefore I'm going to use the fixed effect model. The only way that you can use the fixed effect model is if the fixed effect model really applies. It applies in some cases, and in those cases it's legitimate to use it, and but in most cases it does not apply, and in those cases you can simply use it because it's going to give you better power. In that case, the fixed effect model is simply not an option. There's just one more option that I want to cover today. Let's go back to scenarios, show scenarios, and let's go back to the original basic design. One thing that we can do is to create a graph, and I think in any power analysis, whether for a simple randomized trial or for a cluster randomized trial, graphs are an incredibly important resource because they allow you to see the big picture. I also think that as you get into more complicated designs, as we are doing over here, the graph becomes even more important. Over here, for example, what the program has done, first of all, is it takes all of the values from the main screen, the fact that we're using random effects at both levels, the fact that the standardized mean difference is 0.5, that the ICC is 0.07, that there are 20 students per group, and so on. The only thing that's different is under number of schools, it says the number varies, which allows it to create this graph. By default, it's set it up so that the number of schools goes from 2 to 20, and we can see how power is affected. In fact, you can see fairly quickly that as the number of schools increases from 2 up to about 7 or 8, there's quite a substantial increase in power with every additional school. And on the other hand, once you pass about 13, adding additional schools has only a relatively trivial impact on power. But within this range over here, you have a number of choices that you can make. For example, with 8 schools, or let's say with 7 schools per treatment, power is going to be 71%. We see that over here. With 8 schools per treatment, by clicking over here, power goes up to about 78%, but the cost increases. We can go up to 9, power's up to 83%, but again, the cost increases. You can actually move this little bubble along just by dragging on it, and to get more detail for each particular point. Something else that you can do is simply click on any point and get information about that. And finally, and this will turn out to be important a little bit later, you have these arrows up here, and you can move this 1 unit at a time. So for the sake of argument, if I wanted to find the first number of schools that would give me power of 80%, I can simply click over here. I see it goes from 63%, 70%, 78%, 83%. So I'm able to find that fairly quickly. I also might want to see how the cost varies as we increase the number of schools. We see that over here, but I also have the option of adding cost to the graph, and so that I can see, as you might expect, the cost goes up in a linear fashion. With every additional school, there's a corresponding increase in the cost, whereas power goes up in a curvilinear fashion. So that, again, going from here to here, you get more of an increase in power than you do in cost, whereas up here you get a relatively big increase in cost and almost no change in power. As I said before, it's in this range over here where where there really are decisions to be made, where the increase of every school costs a certain amount more, but you get a lot of bang for the buck, as it were. The other thing that we want to do, however, in any power analysis, this here is all based on the assumption that the effect size is 0.5. But in general, in fact, always, we don't know that. If we knew what the true effect size was, then we wouldn't need to compute power. As a matter of fact, we wouldn't need to do the study at all if we know what the effect size is. The point is, we don't know the effect size, and what we're saying is, if the effect size is 0.5, this is what our power would be. Well, what if the effect size is 0.4? What would the power be? It would be helpful to have a second line over here that shows what happens if the power is 0.4, and then maybe have a third line that shows what happens if what happens if the treatment effect is 0.4, and what happens if the treatment effect is 0.6. In other words, what if the intervention increases the mean score by 40 points, or 50 points, or 60 points? What would power be in each of those cases? Come over here, click on Series, we click on D. The program shows us that initially the effect size, the standardized mean difference, is 0.5. We're going to add another box over there, which gives us the option for putting in 3 of them. One of them is 0.5, we wanted to leave that. One of them is 0.4. One of them is 0.6. I'm going to click OK. And what happens immediately is we get 3 lines. Down here we have a legend. The top line, obviously the one with the greatest power, is for an effect size of 0.6, a 60-point difference. The middle one is for a 50-point difference, and the lowest power is for a 40-point difference. And again, what we can do, since we originally were thinking of working with an effect size of 0.5, we can click on this line over here, and let's come back to the place we were before, where we were working with 11 studies per group. We're assuming that the power is 0.5. And let's say that we decide to power the study for this. In other words, we're saying that if the effect size really is a 50-point difference, and we're going to have 11 schools per treatment, then we have a 90% chance of getting a statistically significant result. If this is the number of schools that we go with, what if it should turn out that the effect size is really not a 50-point difference, but it's only a 40-point difference? In that case, what would be our chances of getting a statistically significant result? And to find that out, we can click over here, and we see that in that case, we would have only a 75% chance approximately of getting a significant result. Now, we might make the decision that, well, you know, if this really increases the mean score by 50 points, that's really an important difference, and we really want to know about that, and we will have a 90% chance of getting significance in that case. But if it only increases the score by 40 points, well, that's important. It's not really important enough to power the study for that. In other words, it's enough that we have, in that case, a 75% chance of getting a statistically significant result. So we're going to work with 11 schools per treatment. On the other hand, if the treatment effect is even larger than that, if it actually increases the mean by 60 points, then we're going to have almost a 98% chance of getting a statistically significant result. So that's quite good. So that's one position that you could take. Alternatively, you might say, well, I had planned to go with 11 schools per treatment. But if I do that and it turns out that the effect size is only 0.4, then my power is only 75%. And even if it only increases the mean by 40 points, that's pretty important. I would not like to miss that. So I'd like to have at least 85% power for an effect size of 0.4. So what you can do then is we've highlighted this blue line, and you can use these arrows over here to move to the right, and we see that with 12 schools we'd have power of 78%, with 13 we'd have power of 82%, and with 14 we have power of just about 85%. So maybe we decide to go with that, and if we're powering this to have good power for a 40-point difference, then in the event that the difference is actually 50 points, power would be better. And to find out what power would be, you can click over here. But another way to do this, especially as the lines come close to each other, is now over here, rather than simply having arrows which move that little highlight left and right, we have arrows also which move it up and down. So I can click on that, and I can see that in this case, power for a 50-point difference would actually be 96%, and power for a 60-point difference would be better than 99%. And I might decide that this is what I want to go with. Assuming that this is my decision and this is the chart that I want to include in my report, I can say edit, copy the graph to the clipboard, and then I can open up a copy of Word and click on here and press Control V and paste this into Word, and now I have a copy of this running in Word. Something else that I can do is, if I wanted to, I could actually export this to Excel, and the way to do that is I can go to Show Table, and what I have over here is a table in Excel format that parallels all of the information on the screen. And in fact, these run in tandem. So for example, at the moment, we see that in Excel, we've highlighted the place where we have 14 schools, an effect size of 0.4, power is 0.84, the cost is $84,000. If I was going to come back over here to one of my original things, and I'm going to click over here where the effect size is 0.5 and we have 11 schools, again, the Excel spreadsheet has now focused on that, where power, you will remember, is 90.4%. The cost was $66,000. We see that over here as well. Conversely, if I click on something over here, we'll find that the graph keeps up with this. And finally, and perhaps most important, we can save this table. We say File, Save Table. We give it a name. And then I'm going to close this and close this. I'm going to open up a copy of Excel, and this actually appears on my recent worksheets because I was working with this before. And you see that here in Excel we have all of the information for a standardized mean difference of 0.4, 0.5, or 0.6. We have the power. Down here we have a table of the costs. And critically down here, we have a list of all of the other assumptions that we're making about the statistical model, about the ICC, and so on. And those of you that wanted to could then take this and create a graph in Excel and use that for whatever purposes, for including in reports and so on. Okay, that's it for this week. Please feel free to email me any questions. For those of you that are taking the course, the easiest thing to do is to post them to the board. I check that a couple of times a day, and I look forward to looking at your queries and answering them over the course of the week. Thank you very much.